Yeah,
If it were free, I'd definitely go with the higher level.
Yeah.
But,
there's always open MIT courseware.
is there? Yeah, right.
Yeah, you can do just about any topic through that website.
But I like this, programmer, he had no prior experience in programming. He
Mhm.
would just go to a Harvard or MIT with a backpack and a hoodie. He's like, no one cares. I went to classes. I just didn't get a degree.
That's awesome.
It's just going to class. Not going through a degree, he just going to math. It's pretty interesting.
Well, I guess we're about there. Welcome back, folks. Well, we've got an even split, 3 in person, 3 in Zoom. That's how my last class was as well. And it's official. We can get started. Any questions at all to start us out, folks, today? Okay, well, the plan for today is a lighter topic, and we deserve it. We've been working hard, especially on that very last section. 10.1, we're getting into curves described by parametric equations. But it's a kind of a fun topic once you see how it works. We're going to use technology, Desmos, to illustrate how some of these curves plot. And then, well, section 10.1 is more about plotting them and putting them in different expressions. But it's a pretty short section. We'll probably as well today look into doing some calculus on this new kind of setting. We'll look into things like how to compute a derivative, a tangent line equation, looking into concavity, area under the curve, the length of the curve, just your standard kind of topics. So this is kind of a nice rehash of Calculus 1, but in a kind of a radical new setting in a way. And kind of the purpose of chapter 10 is that's basically what you're doing in Calculus 3. It's not necessarily always these functions. Oftentimes it's a function of multiple variables with a real number output. And you're just redoing all of the stuff you did in Calculus 1. Instead of a tangent line, you want to compute a tangent plane, for example. Instead of the area under the curve, you want the area under the graph of the function, which might look something along these lines. Our function f of xy equals z can plot as a surface. Here's my best attempt at drawing the surface. Great Calculus 3 instructors are also great artists, it turns out, or great at coding to draw these on their own, because now you're looking at area under a surface like this, not necessarily a plane any longer. So we're doing similar things, but we're still in one dimensions. It's just that our curves don't satisfy the vertical line test any longer. They're not graphs of a function y equals f of x, but they're still functions working up for us. There's just now multiple functions at once. Not sure why I did that. Let's bring that back. So that's what chapter 10 is all about. We'll finish off 10.1, making this the last assignment for the course. And then we'll just go for selected topics out of 10.2. On closed week, we're going to be mostly reviewing. We're just going to finish off maybe 1 or 2 topics from here. Then immediately convert over to reviewing for the final exam. So we're in 10.1. Let's give this a try. Here's how it starts, just one big definition. And our goal now is just to understand what's going on in this brand new setting. So a parametric equation, and polar coordinates is the name of the chapter 10. We're going to be dealing with first ordinary kind of parametric equations. We'll take values x and y, just like a coordinate xy in the xy plane. But now we're going to say x varies according to a new function f, and y varies to a new function g. We want these functions to be continuous differentiable if we're going to be working with calculus on here. But the first thing we want to do in section 10.1 is just get familiar with this new setting. So here's what a diagram could look like for this setup. An initial point is going to be given as f of a, g of a, but that's because the parameter is t itself, and it ranges from a to b. So starting off at a gives us the initial point. Let's place it right here. Here's our initial point. We can call this t equals a, but that's not the point, right? That's just telling us the parameter value that gets us to the point. At t equals a, we land on the point f of t, rather f at a, g at a, And then the curve could do just about anything. It doesn't have to obey the vertical line test. It can intersect on itself, for example. It can completely backtrack on itself, which is something we have to watch out for if we're looking for, say, the length of the curve. But let's just draw something kind of generic. The curve could look like that. So this is our initial point right here, because this is where the initial value A is. The actual point is on these coordinates, f of A, g of A. Not quite x and y any longer, but really it is in spirit. We're just emphasizing the functions this time as we go to calculate this. And another thing that's new for parametric equations is that there's a directionality here. If this is the initial point right here, and this one's the terminal point, the curve is swept out in this kind of direction. Again, it might backtrack on itself depending on what happens with the derivative of these functions. But for most functions we're going to look at, it's going in a particular direction like that. Automatically failing the vertical line test means you cannot specify this as y equals f of x. It's just impossible. But throwing in two functions, you can specify this curve in that kind of way. So we have a terminal point when the parameter takes on the value b. So this is at t equals b, giving us f at b, g at b. Let me match up the highlighting here. And so this coordinate is g of b for y. And right down here, f of b for the x coordinate. So this is the new setting that we're going to start studying calculus under. Any questions whatsoever with the diagram so far? Okay, so the interesting thing that happens here is every value of the parameter t that we select, sometimes it has a finite range in length rather, like we see here. Other times it can take on any real number whatsoever. But every value of t, like we've indicated, is going to give us a point. So if we just go to some random spot in this curve, this might be for t equals c. C has to be between a and b. And it just gives us a new point, f at c, g at c, which specifies the x coordinate and the y coordinate altogether. So kind of a radical new setting. And this really contains lots of interesting applications. One applications on the notes in section 10.2 is just tracking, say, like an elementary particle in the Large Hadron Collider, any kind of setup like that. It might be specified like this, but maybe there's going to be an x, a y, and a z as well. So this can be done in 3 dimensions or any dimension n greater than or equal to 2. So that's how parametric curves are described. For dimensions 2 and 3, we can plot them visually, and at higher dimensions, we just have to work more a little bit analytically. And to get a feel for some one of these curves, here's a really interesting curve to plot. It says we won't do this one by hand. We'll do 2 by hand plots, but we're going to use technology to plot this one. And this one happens to have a name. It's called the butterfly curve for reasons I couldn't tell you just by looking at the format. But the x-coordinate is indexed by the parameter t, giving us all that information, and same for the y-coordinate. Let's give this a try. Desmos turns out to be really powerful for plotting this kind of curve. It's also doing a great job for, if you know you're taking Calculus 3, it does a good job of plotting surfaces as well these days. The way we put in a parametric curve is by going like this. There has to be a function for x and a function for the y-coordinate. So let's just throw in something generic first. We want to use the fact that we're dealing with the parameter t. So let's go maybe t squared. And, well, did a good job plotting that. Other things we might want to do is decide on how much we want, what domain we want to range this on. So if we're going from A to B, we might select 0 for our A value. And let's add a component, a slider, for B. Then let's redefine this. We want B to start at whatever A is. We set it to 0. And then just give it any upper bound that we might want. Let's go for, how about 100? Step size at 0.1, something like that, just makes the curve seem like it's continuously generated instead of lurching forward at unit 1. So if I scroll this all the way back to 0, this parametric curve that's setting x to t, y to t squared goes like this. It just gets swept out in that direction. Not too interesting, maybe. What if you put in cosine t? That always gets interesting because of the oscillations that happen there. And nothing too wild on that one, though. Let's maybe extend this to sine t. Now we're getting a circle. If we put in sine t squared, I'm not too sure what happened there. I think the technology failed, or so many oscillations that it kind of got messed up on a t squared. This is some really unstable plotting. This is not the real graph. This is Desmos trying to connect the dots, but too much going on here for sine of t squared out of nowhere. Wasn't expecting that. Same with power 3. But now what we want to plot is that curve down below. So let's throw this in. So we'll start with sine t. Add our slider for t. Oh, hang on. Sine t and t. There we go. We've got our basic behavior back. Let's move that around so we can see a bit of the curve. Maybe zoom out a touch. Maybe that's what I should have done for those other plots. So we plot sine t and t. This is how this curve plots out. Sine t is giving us an oscillation, but the second coordinate is getting higher and higher. So it looks like just a sine wave on the y-axis, kind of a curious drawing. But now let's start adding in extra information. This is multiplied by e to the power cosine t. So now it got pretty wild just based on that. Then minus 2 cosine t, or rather cosine 4t. Remember, this is supposed to be a butterfly curve, so not sure if I see a butterfly just yet. Maybe let's wind this back a little bit so it doesn't get too complicated. Then the next part is sine power 5. For sine power 5, we got to throw it in this way. Sine t over 12. Close that parenthesis, raise it to the power 5, and it'll come out correctly.
Should this be subtracted?
So, oh yeah, absolutely. Thanks for spotting that. A minus right there. I kind of improved the drawing a little bit with that one little change there. Kind of cool thing about Desmos is you can see the changes with each one of these small little changes or additions and subtractions. So it looks like we got the x coordinate in sine t e to the power cosine t minus 2 times cosine 4t and so on. And the next coordinate goes cosine t. Something's happening in there. It's not exactly a butterfly still. But this factor looks like it's directly equal to that factor. So there's a shortcut we can use. Let's copy from, close that parenthesis, copy from here. Hang on, it doesn't seem happy. Let me look at my delimiters here. I have 1, 2 open. And then, no, I have 3 open. My power 5 should be, it seems like the right match on parentheses. Does that look all right to folks so far? Let me put in this next portion. I'm trying to copy paste this, but it's being kind of a pain. I think I can copy to there. Now for cosine t, go times. I think I got that parenthesis. Close all these parentheses. Hang on, I think I have some weird parenthesis mismatch there. And this is supposed to be the butterfly curve. Let's see what it does as we extend this parameter. So right now, t is just set to 0. There's one point. We can kind of see it. I don't know if that even shows up on the projector. But there's a point there, depending on your vision, how great it is. As b gets larger, it starts to extend out. And let's zoom out a little bit on that. Supposed to be a butterfly curve, and I think I might have typed in something in there just a little bit off, but it's supposed to be fully symmetric. Sort of is looking like a butterfly at the moment. But let me look at my parentheses. That looks really kind of awful so far. Cosine t, 2 open parentheses. then two more open parentheses. At 5, I should be closing one, then closing the second one to match up with that. I have to have another one closed from up here. And Desmos is saying one more. Let me see, 1, 2, 3, 4, 5 open, and then 1, 2, 3, 4, 5 closed. Something about the way I type this in is just upsetting Desmos, I guess, but I think we've got it. Maybe there's an extra parenthesis here. There it was. That one parenthesis just threw it all off. So let's look at this again. Hardest part about this is just typing it in, of course, but once we have it in, if you ever played with something like a spiral graph, this is kind of what we're doing right here with this sort of problem. It gives us this really interesting shape, and there's a lot of different curves like this with different given names. Depending on how creative you want to be with this, you can draw just about anything using parametric equations. You could draw a Batman symbol if you want. There's a crazy equation that when people write it down, the equation gets plotted here at the same time. So it's like a self-referencing parametric equation that people have come up with. There's like no limit to your imagination on this kind of stuff. So that's what's going on with parametric equations. And we're going to use Desmos as a tool to plot these just as a big assist, but maybe for some simpler problems. Here's the next problem we're going to give a try on. This is the tedious part of the assignment. The best way to get a really good handle on parametric equations is you just have to plot them. So bear with me. We're going to do a couple by hand plotting on these kind of problems. Then once we plot these, we'll use this tool just to see how accurate our plot came out as. So let me put in, well, let's start with the plot first. Interesting thing about this plot is we don't want to start with a table XY. We want to start with a table that goes parameter T first, because that's going to say what points you really pick up. Then we're just plotting X coordinates and Y coordinates. So you can say X is 1 minus 2t, or just an X on this column. Y equals 1/2 t minus 1. And if we're about to plot these two equations, any predictions for what the plot is going to look like? Would you predict a parabola, a circle, a line, or something just crazy like this one over here, the butterfly curve? Kind of hard to tell, right? One thing that we might say, though, is if it's linear here and linear here, probably all we're plotting is a line some way, somehow. And that's part of the work that we're going to do here, is to try to determine what is it that we're plotting. For example, on this one, X is sine squared t, Y equals cosine t. This one isn't a line. It's kind of hard to determine what these should really come out as. But the more we plot them by hand, the easier it is to see how this is all coming together. So we go first put in the initial point using parameter -2. Then it's just a bunch of computations. We have a value of 5 when t is -2 here. -2 here is going to give us a -1 minus 1. So -2 again. And then just use your best judgment on how much to increment the parameter by. I wouldn't want to go to, say, -1.5 next. Let's go to -1. If you went to 0, that'd be okay as well. Try to go for around 4 or 5 points. I think the homework says go for 5, but as long as you have around 3 or 4 points and you can see what's going on, you're probably okay. At -1, this time we're going to get a 3. This time it's a little bit more annoying. We have -1/2 minus 1, so it's going to be a -1.5 on that one. Update the parameter to 0. We'll get a 1 for X, -1 for Y. Now the parameter is 1. Now it's 1 minus 2 for a -1 on X. This time it's a 1/2 minus 1, so a -0.5. But look what's happening to the Y coordinates. They're changing, they're increasing in just a normal, predictable way. Means there's a slope here, right? It's increasing in the same kind of way the X value is increasing. So let's finish this off, put in value 2. This will be 1 minus 4t, so we have a -3 on this. 2 here is going to give us a 0. Might as well put in the 3 value. It's tempting to skip to 4 on this one. At parameter value 3, we're going to get 1 minus 6, so a -5. Then this is 3/2 minus 1, so we're at a 0.5. But even if we were kind of imprecise with our arithmetic, we have some predictions on what these are coming out as, right? This should be a 1. This should be a -7 at parameter value 4 if the pattern is maintained. Let's just double check. This is 1 minus 8, so yeah, -7. Or here is going to give us a 2 minus 1, so it's definitely a 1. Now look at the coordinates. X is in negative and positive values, same for Y, so we might as well just put in all quadrants on our plot. And now the order we plot these points is important as well, because we want to indicate the direction at which the curve is traced out as the parameter value t is traced. So that's the new thing about this kind of plotting. The direction is also important here. So this one is our initial point. Let me make sure I match up the color coding here. Initial point looks like it's green. So we're going to start at that initial point. This one will be the terminal point, which we used in blue, and here's how they come into play. We got to go 5 units to the right, 7 units to the left. And the range on Y is not too impressive. I'll go a little bit bigger scale on the Y axis. So from -2 to +1. And then we just get to plotting. At +5, we're at -2. Then at 3, we're at -1.5. At 1, we're at -1. At x is -1, we're at -0.5. Starts to look like a real circle, and I don't have a steady hand on these tick marks necessarily, or not a circle, but a line rather. So it seems like we are on the right track. So next is -3. Over here, we're at 0. Then -5, we're at 0.5, about that height. At -7, we take value 1. So here's my line. If your line doesn't look like a line, but you know it should be, maybe the tick marks were just kind of uneven. You don't have to redo your sketch. It just has to be correct in spirit. You don't have to be an artist. But we have to just show the directionality. So here's our way we're indicating with an arrow. Just put a little arrow along the line to show how the points were swept out as we plot them by hand. Then that was the terminal point. That's the initial point. Well, this problem is completely done, but even in section 10.2, knowing what your curve looks like is an extremely powerful tool for this kind of work. These problems have a way of being really, really excessively tricky. So after you do the plot, the next best thing to do is, let's see if that really pans out. This will be valuable for when the curves get a little bit more complicated, not exactly like this one though. So let's just wipe out all that stuff. Let's re-go through the method of doing this parametric plot in Desmos. First thing you do is just put in coordinates like this. For the x coordinate, just directly type in 1 minus 2t. For y coordinate, just drop that in, 1/2 t minus 1. And we have a range on what t is allowed to take. So for the initial point, take in parameter value -2. And to show as a kind of dynamic picture how this was swept out, we want to put a value b here. B is going to go up to 4, but start at -2. So once you add b here, at the slider, click on where b is, and put a -2 up to the parameter that takes us to the terminal point, +4. And 0.1 does a good job on that. So with that all set up, here's what our curve looks like through technology. There's a red point right there, so that's the initial point. And as b increases, this is essentially the parameter value increasing, and it sweeps out the curve in this kind of way. It's kind of lurching forward, but we're ending, well, I can't quite click on this to get a value. It doesn't have the same behavior as normal Desmos, but it looks like we ended at -7, +1, and we started at 5, -2, which matches up with our drawing right here, or the table if we're looking at that part. So think of example 2, part A as just kind of a way to get into plotting these things. and also learning how the Desmos tools will work if you decide to use it. Any questions at all, folks, with this one here? Okay, so if both coordinates are just linear functions, we should expect a parametric plot, which is just a line segment. If there is no bounds on this, it's an ordinary line, like we would plot a y equals mx plus b, for example. But the good thing that this can provide is we can now give a function, well, a parametrically described description for a vertical line, where that's not something you can really do with a y equals mx plus b. That would have undefined slope, for example. So now let's try this out again, just for the extra practice. This is the last one, doing this kind of process. But first, any predictions on this one? If you have a sine squared and a cosine, what kind of curve would you all say this is? If your answer is you have no idea, I totally get it. Neither would I, but sometimes it's good to kind of guess on these. So it turns out on this one, this is my claim, this one's a parabola. And it's really weird why it would be a parabola, but there's two ways to tell. One way is to just ditch the parameter t altogether and solve for this as a Cartesian coordinate type of equation. And we could get a parabola that way. Let's in fact do that after we do the standard thing of just plotting it and see if we find a parabola. So on this new one, here's the new table. We have a t parameter, but now we're using a whole bunch of trigonometry. It's going to start at 0. And x is just going to be sine squared, so only positive values. And y is going to be cosine t. On the range from 0 to pi, cosine t is going to take both positive and negative values. So it looks like we're going to have something that goes like this for our plot. X coordinate only being positive, but y being positive and negative on that range for the parameter means we need quadrant 1, quadrant 4. Not looking like a parabola, but parabolas can also open this way as well, so it still has a chance. So let's start plugging values. At 0, sine is 0, so is sine squared. Cosine 0 comes out as a 1. Now we have to make a judgment call. We do pi over 4, we're getting about 4 points. We do pi over 6, we're getting about 6 points. Let's go for a pi over 6 just for a little bit extra information on this. Pi over 6, well, we're going by 30 degrees, coming up to 180 degrees, in other words. At the pi over 6 value, sine at pi over 6 is 1/2, so squaring it is a 4th. Let's write it as a 0.25. Cosine at pi over 6 is a √3/2, which is approximately a 0.9, rounding to the nearest 10. Rounding some of these because our goal is a by-hand plot. I don't need the exact figure, I just need the ballpark of where it is on the by-hand plot. Then 2 pi over 6 is pi over 3. At pi over 3, sine is √3/2. So if we square that, that's 3/4. So a 0.75 on that first value. Cosine at pi over 3 is a 1/2, so a 0.5. Then next it's 3 pi over 6, which is just a fancy way of saying pi over 2. And at pi over 2, sine is 1, so square of that is 1 again. And cosine at pi over 2 is 0, so we'll just throw in the 0. And now the cosine values are going to be negative, but the same values right here. We have the table essentially replicating, but different sign. We'll still be careful because we're squaring values over here. It's harder to see that pattern. So go to 4 pi over 6, which is really 2 pi over 3. This is kind of a trig review out of nowhere. Sine at 2 pi over 3 is the same as sine at pi over 3. Pi over 3 is a reference angle. So if we square that, we still get the 0.75 right back. Cosine at 2 pi over 3, however, is negative. This one's a negative 0.5. Now, almost there, 5 pi over 6, already in reduced form. Sine at 5 pi over 6 is still a positive 1/2, so the square of it is 0.25. Cosine at 5 pi over 6 is the same as this one, except it's negative. It's in quadrant 2. So we'll say negative √3/2. approximately negative 0.9. And finally, it's 6 pi over 6, which is just pi. This is an easy value here. Sine at pi is 0, so is its square. Cosine at pi is a -1. And so these are our values we're going to be plotting. This should look like a parabola, but let's be careful on how the points are plotted. This will be the initial point. This will be the terminal point. So let's maybe start by setting the scale. In the x direction, we're going from 0 to 1. And in the y direction, we're going from +1 to -1. So I have the scale kind of extended on the horizontal direction, slightly compressed in the vertical direction, but you're allowed to always do that kind of adjustments. In fact, that's what calculators like these often do. If we change this around, we could rescale it, make the line look steeper out of nowhere. So the plot points are going to plot first at a 0, 1. So we're up here. Then a 0.25 is going to be, hang on here, pi over 6 is 1/2, and 1/2 squared is 1/4. So yeah, 0.25. And then at 0.9, let me put in some extra tick marks here. So this is 0.25. This was at 1. And we get this new point at approximately 0.9 in the y direction, at 0.25 in the x direction. That's 0.75, 0.5. So here's our half. Here we get 1, 0. So if this is a parabola, this would be like its peak so far. And now it's 0.75 for the y direction, -0.5, excuse me, 0.75 for the x coordinate, -0.5 for the y coordinate. It's kind of funny, these coordinates are kind of hard to see from the out of nowhere just because there's so much information to look at. Then 0.25, we're at -0.9, so down here. Lastly, the terminal point at 0, 1. And the way the points select out was in this way. Not the best looking parabola, should be a little bit more rounded out over here, but again, it doesn't have to be perfect. The directionality went in that way. And so we really are looking at a parabola on this one. Pretty strange how sine squared and cosine in this kind of way gives a parabola. If this cosine right here was squared though, it would have been a circle instead, which is also kind of strange with these equations. Any questions at all, folks? Showing the plot? Okay, let's, instead of throwing into Desmos, we'll do that in some of the next problems. Let's show if we can really find the parabola on this by doing the process of eliminating the parameter. If we do that, we'll get an ordinary Cartesian equation for this description. It'll be an x equals something involving a y squared, because this is a parabola opening to the left, centered at 1, 0. So the way we could start that, limiting the parameters sometimes is kind of weird algebra, but if it's a trig problem, you automatically want to think in terms of sine squared plus cosine squared is 1. This would allow us to rewrite x equals sine squared t as x equals sine squared t is 1 minus cosine squared t. But that brings in the y value. Y is cosine t. So x equals 1 minus y squared. So in a weird way, use the sine squared plus cosine squared is 1. Then just substitute in if y is cosine t. Then for cosine squared, we have y squared. And that is the right equation. The 1 here tells us the parabola moves up to that point. The negative here says it's opening to the left in that direction. We've got it, folks. Not only do we have the plot, you don't have to do this unless the problem is specified. But this is a good one on getting started, since that's going to be the next two problems we'll take a look at. So kind of weird. Sometimes, like for the butterfly curve, you don't want to eliminate the parameter. That's going to involve probably way too much work. But other times, if you want more intuition on the parametric description, you can make that happen. Now for this problem, you could use ordinary calculus methods on differentiation, integration. You just would have to make sure your integrals, for example, have a dy on the end rather than a dx. So we're going to look into this technique a little bit more just to get some more intuition on these curves. by limiting the parameter a couple more times. But we now have some predictions. If you have an x and a y like this one, this should just be a linear equation, so that can help us out get started. And what's really nice about the methods for a linear equation is eliminating a parameter is just solving for the parameter in one equation, substituting back into the other. There's a lot of ways you could do this. You could solve it here, t on the equation for y, and now you'll have a curve described as x equals something. I want to solve it for x because now I'll have a function y equals f of x. It just makes it feel more familiar in our calculus setting. So step one is just to solve here for t. If x equals 3t plus 2, then that would mean x minus 2 is 3t, and so x minus 2 over 3 is t. And we take that information and just directly drop it right inside there for the y coordinate. So y equals 4 times, here's the value of t we found, x minus 2 over 3, and then just a minus 1. Let's do just a little bit more algebra. It'd be weird to stop right here. If we distribute 4 and divide by 3, we get 4/3 x minus 8/3 minus 3/3. So y equals 4/3 x minus 11/3. So my claim is this is the same plot on the xy plane, but now no parameter. It's just x and y. So we have definitely eliminated the parameter in that sense. But sometimes it's really hard to tell if we have the right equation. The algebra here can be strange, like in part B, it's going to be pretty strange. So let's use Desmos just as an extra verification. We've got the right equation. Any questions first at all on solving this one? Okay, so I'm going to focus on this part right here. Notice there's no bound on the parameter, so it's any real number whatsoever. So if that's the case, let's go for the starting value, just something generic like -10. Click over here, go -10, +10, any kind of value, -100, +100 here would do just fine. Throw in the specific values we have, 3t plus 2. And then for the second coordinate, 4t minus 1. That's going to be our curve. But let's see if we eliminate the parameter correctly. The trick here now is go to the equation that we derived here. If this is wrong, we're going to know right away when you go in and plug y equals 4/3 x. Already there's a big mismatch, but let's see if the y-intercept comes out correct. Minus 11/3. This is what we want to see, a total overlap with the parametric description from up here, as well as the description down here when we eliminate the parameter. This gives us huge numerical evidence that we did do this correctly. Doesn't mean it's the exact right equation. Maybe you zoom in and there's going to be a separation after some point, but that seems pretty unlikely. Well, that part A was kind of a warm-up portion. We have a couple more to take a look into, but part B is really tricky out of nowhere. We'll spend some time on this one. Let's start with just a prediction of what we're looking at on part B. The equations look kind of confusing, and it's hard to guess what this curve is. Just plotting it can give you a lot of information. So let's start on the plot on this one. I'll kill the equation y equals. Let's first work with the bounds on t. This one has t starting on 0, ending on 2 pi, but we can still leave the parameter b here. Click on this window, and you want the initial point on that cell and the terminal point on this cell. You can directly type in 2 times pi, and it'll know what you mean. Let's add a little bit more fine control on that. Finally, x-coordinate is cosine t plus 1. And we already have some of the curve. Let me make sure we're zooming out well enough. Kind of a weird thing this one does. It just goes up like that. But this is based on what b is doing. We don't have the whole thing in there, so let's put in the second part, sine t minus 2. Out of nowhere, we have a circle, and the minus 2 just adjusted where it is. So this description we're looking at X is cosine t plus 1, y equals sine t minus 2. This one looks to be a circle out of nowhere. It looks like it has radius 1 unit and that it's centered at +2, -2. So if we eliminate the parameter, we should be getting the equation of that circle right there. Let's give it a try, but any questions first with the plotting of this? Let's just move that around just to double check it didn't wrap around twice or anything weird like that. Okay, so here's the process. We want to find the equation, but you have something like this. We're definitely thinking in terms of trigonometry, and we want to match this approach as well. We were using sine squared plus cosine squared as 1. That was the fundamental trick on this. And it still works on this one. It's just a little bit more messy this time. This time we start by taking x squared plus y squared. And that makes sense because x squared plus y squared equals r squared is the description of a circle of radius r. So we're starting with the right component to get a description of a circle. But now here's where the algebra gets really interesting. If we're squaring x, means we're squaring this value, cosine t plus 1. And then the square of y is sine t minus 2 squared. Our job when we do this, expand everything out, is look for the cosine t plus 1s. We have to eliminate it and plug in an x in that position. And then also look for sine t minus 2, anywhere it occurs, because we'll plug in a y for that value as well. So on the left, x squared plus y squared. Here on the right, we're going to start expanding. So this is a cosine squared of t plus 2 cosine t plus 1 on that expansion. And then same idea on this one, plus sine squared t minus 4 sine t plus 4. Well, we've got some stuff here. We can separate out a cosine t, but one thing you might have noticed already is that's really important, right? Oftentimes, if you see a cosine squared and a sine squared, the very first thing you want to do is just combine those to get your plus 1 on that. So this is x squared plus y squared equals, I'm going to skip to 2 cosine t. Then it's plus 1, but the highlighted part is also plus 1. So I'm just going to go to plus 2 on that one. Does that make sense to folks on getting from the 1 to the 2? Awesome. Let's take a look at, well, let's keep on going actually before we get too sidetracked. So I've re-expressed the 1, combining the highlighted parts, getting a 2. And now we're at this last bit, minus 4 sine t plus 4. Now let's pause right here. X was cosine t plus 1. We have 2 cosine t plus 2. But that's good. That's just a 2x. Let's write that in. If x is cosine t plus 1, then 2x is 2 cosine t plus 2. So we have something we can throw in just right here already. That's just a 2x. And same trick actually applies with the y coordinate as well. If y is sine t minus 2, but we've got -4 sine t plus 4, looks like this was just multiplied by -4, that whole entire equation. So let's rewrite that. -4y equals -4 sine t plus, oh, hang on, what am I doing here? -2, thank you for that. That should have been, yeah, hang on, this seems to be a little bit off. We have a 4 sine t plus 4, and that was a -2. I know what we can do. Let's just separate out some of these values. If the 4 is not working, let's call this +2 plus 2. That should work, right? Let's give that a try. So x squared plus y squared equals, let's do a substitution here just to eliminate the white noise on that part. And then go with its -4 sine t plus 4, it's also -4 sine t plus 2 plus 2. So we multiply this by negative, see, -4.
Change it to +8 - 4.
Yeah, good call on that one. I didn't want to separate that out. Let me finish the multiplication here. That could actually help us out a little bit. We saw the -4, and so now we're multiplying this by -4, but that's a +8. Yeah, good call. If we were looking at that on the onset, it would have informed how to split that coefficient. We're not splitting it in that kind of way. We're going to go exactly as you said. +4 is the same as +8 - 4, and that +8 has to be there from this part. Now we're all set up. -4 sine t plus 8 is what we see here, but that's just a way to write in. Looks like I forgot a copy in that value. I was multiplying the left side of the equation by -4, so it should be a -4 here as well. So this whole thing up to that value is just a fancy way to say -4y. So let's rewrite this again. We've got x squared plus y squared is 2x minus 4y minus 4. And we can do even more work on this thing. Equation of a circle has certain standard forms. Let's go for the standard form for the equation of a circle. What we want to do is bring in all variables to the left-hand side to get to that. If we can find that standard form, it's going to reveal the center and the radius. And then we can just check if it matches up with this center and radius. So let's take x squared minus 2x. Give it a little bit of space before you go plus y squared. Actually, let's leave the sign off. We could change the sign. We're going to leave a bunch of blank space right here and fix it, but go y squared plus 4y coming from that side. Give it a little bit of space before equality and go -4. Now, the next trick is kind of like a walk down memory lane in a certain sense. What we're doing here is we're completing the square twice. And the fundamental equation that does that for us is b over 2 squared. This is one b coefficient. This is the other b coefficient. So divide this by 2 and square it, and it's a +1. Divide this one by 2 and square it, and it's a +4. Now, the variable x is a guaranteed perfect square polynomial. It factors as x minus 1 squared. Small mental break, go to your mental chalkboard, expand that out, and yeah, we would get -2x plus 1. Same trick applies here, but I need a sign. Don't forget the sign right there they omitted. This will be plus y plus 2 squared equals, not quite -4 here. Remember, we have to balance the equation. Looks like I kind of forgot on that line. Go +1 to balance the equation, +4 to fully balance the equation. And now our right-hand side is exactly 1. That's the right format that we're going for. If you think of it, the vertex form of a parabola where x minus h actually gives you a positive h for a coordinate, that's what's happening here, but for both coordinates. Center is at coordinate xy equals, take opposite values, +1, -2 on this one. And for whatever this value is, it deserves some highlighting. We have to square root it to get the radius, but this is just a lucky problem. It's 1, so no change. But just for the sake of specifying this correctly, radius is the square root of whatever emerged on the right-hand side. So for our problem, it's just a radius 1. Then we double check. That is what we're looking at. The radius is 1, we can tell. And the center is really at coordinates 1, -2. But kind of a weird problem to get down to there. From the parametric description down to the Cartesian description, this isn't even one function. There's 2 functions in there that we'd have to solve. We really try to isolate y. So sometimes these are better descriptions. Trying to get it back down to the Cartesian expression is really, really messy, like this problem is illustrating. But it's good to know that we can do it in this kind of problem as well. Any questions at all, folks, getting through this one? Okay, in the homework set, the last homework assignment for the entire semester in 10.1, there is a question like this one, but if you did stop, say, right here, or hang on, if you stopped right here, that'd be okay with me. Complete the square just if you want to really verify you've got the right plot, like we were doing over here. Well, looks like we have just one more on these notes. Let's take a look at it next. X is t squared plus 1, y equals 2t plus 3, from -5 to +5. This one ought to be another parabola as well. The good strategy on this one is, the moment you see degree 1, we're just going to use the same strategy we did in part A. Isolate t on this equation. That highlighting did not take for whatever reason. So let's go y minus 3 is 2t. Then y minus 3 divided by 2 is t. Then at that stage, we can now just plug in the value for t right here where it's being squared. X is then equal to parameter t squared, but we solved the linear equation and got y minus 3 over 2. Then it's a plus 1. This format already is showing, looks like it's just another parabola, and this one's centered, well, I don't know where it's centered for the vertex, but another parabola opening probably towards the right on the horizontal axis. So continuing forward on this, we have 1/4 squaring the denominator. Numerator squared is going to be y squared. You know what? Actually, let's leave it like that. Why expand that out? This is now in vertex form. Expanding it out is kind of hiding information. And go plus 1. So this is a parabola opening to the right. It's opening to the right because the coefficient here is positive. And the center, not center, vertex, I keep thinking in terms of the circles. The vertex on this one is going to be, take the opposite coordinate, or excuse me, pull in that coordinate for the x coordinate, then take the opposite of this one for the y coordinate. It should be 1, 3. Let's take a look. Again, this is a really, really powerful tool, so we might as well abuse it a little bit if we're learning a new concept like this one. So the values this time, we're going from -5 to 5. Lower bound here is going to be -5. And you could put a +5 here if you like, but I like the parameter b because it allows us to see how the curve is even being swept out. Down here, for b itself, put in -5. And then for the upper bound, go to +5. And this is what we get. Oh, hang on, this is the last problem. T squared plus 1 on the first value. Second coordinate is 2t plus 3. And now as we sweep this out, we're getting something here. Let's take a look. I said the vertex was at 1, 3, and that does look appropriate. It's opening to the right, so it looks like it's the right description. So it's kind of like the world's weirdest way to describe a parabola opening to the right. We can do it parametrically like this, but there's more information. If anything in the physical world has that trajectory, then the trajectory that's being represented here is better than that equation, because that equation down below hides the direction it was actually swept out. This shows the direction. There's actually more information here. Eliminating the parameter hid that information. So that's our new setting. What we want to do is some calculus on these new kind of weird problems. We can't do a lot of problems since we're going to do our last minutes here today. And we'll probably spend about a half an hour when we come back on Monday. I don't want to use up all of Monday on just this topic. We also want to convert over to reviewing for the final exam as well. But any questions at all, folks, with parametric curves so far? Yeah, absolutely. Now we're thinking of a real physical type of problem in that case. In fact, for a really quick application, that's what's going on in section 10.2. Whatever problems I don't get to solving in class, I will post the solutions on. And here's a wild problem. There it is. So this is not necessarily a fully accurate problem for the Large Hadron Collider. This is where they have a huge particle accelerator in CERN in Europe. Things are just whipping around on a track so they can collide the particles, like protons, high energy protons, to see what other elementary particles emerge. And here in this case, t is time. It's in femtoseconds. Everything is really small time intervals if we're talking about these kind of high energy particles. So although the equations might not be realistic, the units actually are for this kind of problem, which makes it kind of fun. Distances in femtometers, so 10 to the power negative 15 in meters. So we're imagining a particle following this track, and these are real questions they would want to answer. How much distance did it actually travel? So these are questions we can't answer by just co-opting our last methods. This is a calculus 2 method that we used ourselves. We had a 1 right here, but if we put it into a parametric equation, it's just now a dx dt and a dy dt rather than the 1. So this is kind of the theme of the notes in section 10.2. Go to a lot of things we've done in calculus 1 mostly, and some of the things we've seen in calculus 2, and just extend it to this situation. Do calculus on these kind of curves now. Even when the curves look really weird like this, that can't even be specified by y equals f of x in one single function. The first major tool we need is, how do you compute the derivative? The author has a pretty big discussion on this, but the first derivative is really kind of nice. dy dx says, you go to this equation and just take dy dt, that's going to be your numerator. Then go to the second, or this equation over here, the first coordinate, and do dx dt. That's kind of a nice situation. If you're differentiating this, you differentiate the y coordinate into your numerator, x coordinate down into your denominator. Here's where it gets kind of weird though. Look at that second order derivative. Dx dt does not change. We're going to take advantage of that. That's pretty weird in a certain sense. The numerator is ddt of dy dx, the original thing over here. This is kind of hard to track because it's such a new setting, but really in a certain sense, this is all we're doing. If you take second derivative of y with respect to x both times, all you're really doing is d by dx of dy dx. This is just a second way to specify the second order derivative in Leibniz notation. But you know, once you've calculated the derivative once, dy dx is just another function. You can plug it into that spot right there. So the d by dx is just that portion. That's kind of hard to separate out. We're going to just reuse the d by dx, plugging in dy dx in terms of y here, and then in here from the first derivative formula. And then this is what we'll get. Kind of hard to track, so let's write this through. So this is going to be, this derivative here is matching up with the d by dx, and the structure goes like this. Dx dt in the denominator. Then derivative with respect to t in the numerator for whatever your function y happened to be. We're feeding the function dy dx into this new derivative, so dy dx emerges here. Does that make sense to folks so far on tracking that formula through on this one? Okay, we have a requirement. We don't want the denominator to be 0. So this will only be valid as a formula if the parameter doesn't take a 0 derivative for dx dt. Another thing to mention here is, when you go to calculate this second derivative right here, this part right here, just the numerator, is often a quotient rule. Not always, but often. And the second thing to keep in mind is, whatever you found for the denominator in the first order derivative is directly the denominator in the second order derivative. That's kind of a weird change as well on this kind of formula. So our author does go into some nice derivations on these kinds of formulas, but I feel like that second order derivative is hard to track through. So let's a second look at it. In these notes, we're going to play around with the first derivative first. I think we have just enough time to try it out. Here's what a typical problem might look like on example one. Gotta not hit the shift key too often. That really pisses off this computer. There we go. So we want to find the equation of the tangent line to this curve right here, where t is ranging from 0 to 2 pi. But we know the first step in this process is just get the slope, right? We need the slope when t is at pi over 4. So we're going to work this problem just fully analytically. We may run out of time, but when we come back to look at it again, we'll also plot it to see if our results even make sense. So here's a step one on this process. Compute dy dx, which looks tough because there's no y equals f of x at all in this description whatsoever. But this is the process. By the formula above on the notes, we do just a dy dx. Divide by, let me fix that, not a dy dx, that's the same problem, a dy dt rather, divide by a dx dt. So even though the formula looks like it's kind of a pain, it's really not too bad. You just differentiate that as a variable of t, put it in the numerator, and same thing with x, put that in the denominator. So this becomes, this derivative here, we just mind the chain rule, it's 2 cosine 2t. And side topic, as far as minding the chain rule goes, a student in class pointed out in section 11.10, part 1, there's a revision on the exercises right here. The revision is a chain rule was missed right here. I had a -1 to a power on that. Alexis Littlefield correctly spotted this error because of using the chain rule. All of your terms or coefficients come out as positive on that. Good call on that one. Yeah. Yeah, that one was plainly wrong. It was right if there was a plus in the equation for the alternating part, but not quite per the chain rule as well. So back to this topic. Sorry for the distraction there. Also the distraction on doing that one on the homework. Derivative of this one is just going to be a cosine t. And so that fully solves our step one. We have the derivative for this curve at any value of the parameter t. But we're interested in pi over 4. So step 2 is telling us the slope m that we're going to use is dy dx, evaluated when the parameter t takes on the value pi over 4. So this is going to come out as 2 cosine 2 times pi over 4 here for the parameter t, and cosine pi over 4 here. So different way to compute the slope this time. That's only because of the variable being t itself. Now in this one, this is cosine pi over 2 altogether. That means the slope is automatically 0. Cosine pi over 2 being 0 in the numerator gives that a result. So when we go to solve this, you might use a structure like this, y minus y1 equals slope m times x minus x1. But you know what? There's a second new thing about this. What is y1 and what is x1? It was never told. Well, it kind of was. It was given to us implicitly because they gave us the parameter and they gave us the coordinates all at the same time. So we can solve that weird new portion as well by saying, to get this and this, go, let's call this maybe a step 4. No, let's consider it step 3. Otherwise, we'd have to wrap back around. Sorry for the weird beeping on this computer. We do x1, y1 equals, the x coordinate is sine t, so we go sine the value of t that we're using, because the tangent line is at pi over 4, has to be pi over 4 here as well. Then for the y1 coordinate, it's sine 2t. So 2 times pi over 4. We'll use yellow highlighting to show where the parameter is going, coming from that initial description. And it's something new and kind of annoying we have to watch out for. Sometimes they give us a point. Now we have to find the parameter, or in this problem, we have the parameter. Now we had to find the point. So x1, y1 is sine pi over 4, root 2 over 2. and then sine pi over 2, that's exactly a 1. This gives us pretty much everything we would like here. Hang on, let me take another look at this. Sine pi over 4, sine pi over 2. So I think we've got the right values, but the slope here is nice, right? It's just 0, so we get y minus the y1 value, 1, equals slope m, 0, times x minus the x1 value, root 2 over 2. So this is just a y minus 1 is 0. And so the tangent line is horizontal at height 1. We don't have enough time to just rush through the plot on that, but that's what we're going to take a look at when we come back next class. We'll try this out again in a different problem, and example 3, which is a bigger challenge because we don't have a parameter. It turns out giving you a point is worse than giving you a parameter on this, so we have to solve for the parameter. But this is a good indication in a nutshell of how calculus is going to work in this new parametric setting. Any last questions at all, folks, on getting through this one? Okay, well, this is as far as the course content can really go in this course. Example 1 can be a legitimate exam question. But I'm thinking of converting over the section 10.2 notes to, I'll select one of these questions to be an actual extra credit question on the real final exam, which means we're reneging a little bit on this one. I indicated on this one, Taylor Series Part 2, we might have this question as an extra credit question, but it was, that's the exercises. It was kind of a painful question that we got through on that set of notes. This one, hang on, still not there, Part 2. Okay, so this question finally fixed some of the mistakes that was made last class, and I said this might be an extra credit question. I feel like it's going to be a rough one. Instead, an extra credit question on the final exam is either going to be one of these examples that we complete either in this class or when we end on Monday before converting over to the review. Something involving tangent line equations or possibly concavity using this second order derivative. Well, I think that's pretty much all I have for folks today. Have a great night and a great weekend. After this class, we're going to be reviewing after just a few more problems here on Monday. But have a great night, folks. I'll see you all next Monday. I think it actually is, to be honest. Calculus 2 is really, really analytical. Lots of stuff with series, but Calculus 3, it's kind of like you're learning Calculus 1 again.
About like areas under, I don't know how you even say it.
Under a surface, yeah, something like this, but it could have waves on it, yeah.
And then it was the surface area function again that you plug in.
Yeah.
Variable.
It's kind of neat, right?
And I
Yeah.
was like, wait a minute.
Yeah.
I hate it because when I was in pre-calculus, my teacher said that the difference quotient was important. And I was like, yeah, that's a little bit.
Yeah.
I like in pre-calc already in high school, and then
Mhm.
I owe her an apology because literally the second you get the calculus. Yep.
Yeah, I get just nailed with that right out of the gate. After a few limits, maybe, but it's coming up fast.
Well, thank you.
Yep. Take care.
My great uncle works at the Large Hadron Collider.
Oh, no kidding. That's really awesome.
Yeah.
That's just an impressive
Oh, yeah.
mankind achievement right there, pretty much.
He only goes there like once every 3 months now, but he used to work there like full time.
Yeah, that's pretty cool.
He's pretty much retired. He's still like, he's also with U Chicago. He's on like 3,000 research.
Yeah.
He's insane.
He must have had fun with all the conspiracy theories that said we're going to create a black hole and end mankind right there.
It's so small of that.
Yeah, they just evaporate.
Antimatter is, it's not, like, it literally just breaks itself immediately.
Yeah.
Well, whatever energy it has, it does not transfer that. I like antimatter because, like, theoretically, that's how you would reach like 100% efficiency with energy. Yeah, theoretically, but like the penetrating power, I guess, is how you can kind of put it, is just so little. Like the second it tries to interact with anything, it just breaks.
Yeah, I see. Yeah.
Would that be okay to like virtual particles and anti-particles? Yeah, it's anti-particles. Yeah. It's like the reason it took so long for us to find out if antimatter reacted in the same way to gravity as normal matter is because like the conditions that we tried to test it with, like it would just break itself. I mean,
Oh, wow.
It was either
Yeah.
that or it had to have some level of electromagnetism, so then it would just skew the results.
Yeah,
Because
darn it.
electrons and positrons is the best way to do it, but it just reacts so easily to electronegativity. So
Mhm.
we finally just made an entire hydrogen, and that finally worked. But there were still a couple like tweaks that they had to do because it just kept on breaking itself apart.
Yeah, that's cool stuff.
Oh yeah, that's insane.
It wasn't that long ago they found the Higgs boson out of that thing too.
Yeah, he was part of the.
He was a part of that
started
team?
Higgs
That's
thing.
awesome.
Yeah. At my uncle's wedding, he got like a text message that they had 6 sigma, so he
Mhm.
was like.
Yeah, that's
he was
like
celebrating
probabilities.
everything.
Yeah, highly significant. That's cool.